So yesterday, Louise was talking about determining whether or not a system of PDEs has this hyperbolicity property that basically, allows us to look at small perturbations around some solution and know that they'll be basically be bounded. That we'll have a well-posed initial value problem. And so basically, he also discussed how the 3 plus 1 system of equations for Einstein's equations doesn't necessarily have these nice hyperbolicity properties. So there are actually a number of ways to sort of address this problem and come up with a set of evolution equations for Einstein's equations that do have better properties. So in your homework, you'll explore one of them is actually based on this 3 plus 1 decomposition and doing a conformal decomposition of that called the BSSN set of equations. So today I'm going to talk about a different way of addressing this problem using a formulation called the generalized harmonic formulation. So, and this formulation actually doesn't use this decomposition into sort of a metric on a time slice and then quantities that tell you how that time slice is embedded in the 4 manifold. We'll just work directly with the 4 metric. Okay, so the basic idea of the generalized harmonic formulation of the Einstein equations is that instead of fixing our gauge degrees of freedom or our coordinate degrees of freedom by specifying these lapse and shift quantities, instead we're going to require that our coordinates themselves basically satisfy an inhomogeneous wave equation. Where they're equal to some functions h of a, which we'll call the source functions. And notice this is not a legit 4 vector. These are just a set of 4 functions, but we'll sort of abuse terminology in this lecture and in some cases treat it like it's a 4 vector.
Sorry,
yeah.
I've seen in some places they do something like define like a background metric you can use in order to make that actually be like a 4 vector, because you define like that box of X like Christoffel minus a background Christoffel, and then that transforms covariantly. Does that make any sense?
Yeah. So if you work this out, this will basically look like something like, and we'll show that in a second, basically something like a contraction of the Christoffel symbol. Mm-hmm. So yeah, again, that's not a 4 vector. But if you basically subtract off something else that the piece that doesn't transform like a 4 vector exactly cancels that out, then you can get something like that. Yeah. But I mean, basically because we want to fix coordinate degrees of freedom, we don't want something that's sort of manifestly covariant. We want to choose coordinates.
Okay.
Yeah, so the main idea is basically going to be that we're going to promote these source functions to independent variables. So to begin with, let's just start with our Einstein's equations, and we're going to write them in this traced reversed form. Basically have just the metric stuff over here, and then the stress energy, the matter component on the right-hand side. So Einstein field equations in the trace reversed form. So the the key insight is going to be that basically we can write the Ricci tensor in the following way. Yeah, so the first term is actually basically just a wave operator. You'll notice, with our metric, ordinary coordinate derivatives act on each component of the metric. So then the second component, I need to explain what that is. So this is basically just if I take a Christoffel symbol and then contract two of the indices. And we can actually just work that out and see that that's that's actually just equal to this box operator acting on the coordinates, and I've just lowered the indice, again, though it's not actually a 4-vector. And then this f is just some function of just the metric and its first derivatives. So basically all the second derivatives of the metric, the sort of principal part of the equations that will determine the characteristics of our PDE are these two terms. So if we just had this term, we'd be very happy. We just have basically something like the wave equation for each component of our metric, and that's sort of the gold standard in hyperbolic equations. But the problem is, this part also involves second derivatives of the metric, right? Because the Christoffel symbols are first, and we take a derivative of that. But so the idea is basically that we can use these source functions to get rid of these bad terms that spoil our hyperbolicity. And so, basically, from this relation, we can directly get rid of that and then arrive at our new way to write the Einstein equations. Yeah, so let me just write them out in all their gory detail. Okay, so, still kind of looks like a mess, but the important point is that basically now in terms of these variables of the metric and the source functions, this term is the principal component. It's the only one that involves second derivatives. And so basically, for the purposes of determining its hyperbolicity, we're just interested in basically the behaviors of this equation. And it is just a wave operator. And so basically, we have a manifestly hyperbolic equation, basically, as long as this metric is sort of reasonable and has one time direction and three spatial and so on. So yeah. So this is basically the generalized harmonic evolution equation, and all we need to do now is also specify some evolution equation for these source functions, because now we're promoting them to actually be evolution variables themselves. So the most generically, we could just write that there's some sort of evolution operator acting on our source functions. And basically, as long as this doesn't, ruin the, basically, as long as this doesn't, involve some higher derivatives of the metric so that it spoils the hyperbolicity of this equation, we'll be fine. In practice, it turns out for, a lot of applications, a simple choice works, where basically you just, require your source functions to be just some function of the metric, and maybe and basically, the simplest choice we could take for this is just what's called harmonic gauge. We just require this to be 0 for all time. Yep, so the idea is basically now our evolution variables are the metric, its first time derivative, these source functions, and maybe their first time derivatives. And then, we know how to evolve if we have the first time derivative of the metric, we know how to evolve the metric, and we can evolve the first time derivative of the metric using this equation star, and then we can evolve these source functions according to whatever sort of gauge or coordinates we want to choose. Okay, but so now we might have a lingering question, and that's basically, say we start in some metric initially, it's harmonic. For example, it satisfies this condition, and then we evolve it forward using these two evolution equations. How do we know that our metric will stay harmonic? We're not explicitly enforcing that. So basically, in general, we want to say, if we define basically some difference between the box of our coordinates and these source functions, which are now independent variables, are we guaranteed to basically have this equal to 0 for all time. So basically, this is now the constraint of our system of equations. If this is not true, then even if we're evolving with this, we're not actually solving Einstein's equations. So the first thing to notice is that if we look at this equation star, and we want to find, and basically we want to include the possibility that these two are not equal, then basically we'll get rid of all these. We'll get rid of all these terms except basically this part right here, or so basically this component here that's just the Christoffel acting on these source functions. Yeah, so those are just the terms we swapped out using this definition of the source function. So what we can notice is that if we basically project this equation using our vector that's normal to our slices of constant t, basically on the left-hand side we'll get 4 equations which are basically going to be the Hamiltonian momentum constraint, right? So if we then can act on this equation with 2 projections onto the time slice, we get the Hamiltonian. And if we do 1 time and 1 space, we're going to get the momentum constraint. Yeah, so basically, if we arrange that initially our constraints are satisfied, then at least we know that if we also solve the Hamiltonian momentum constraint, such that our initial metric satisfies that, then we'll also have that the first time derivative of our constraints will be 0. So now we want to find out how this will evolve with time, right? So yeah, to do that, we'll start by taking this equation here, subtracting out 1/2 GAB times the trace of that, and then we can write that as the following. So we'll recognize that this is just the Einstein tensor. So here's the stress energy tensor. So if I basically take the divergence of this left-hand side, I'm going to get 0 by the Bianchi identity and then 0 by stress energy conservation, right? And then I'll get an extra divergence over here. Okay, so just take the divergence of both sides. And if I do a little bit of algebra to rearrange this, we arrive at this equation. So you can work that out for yourselves. So basically, just using the definition of the Riemann tensor to commute these covariant derivatives and then collect them all into one term. Yeah, so this basically tells us that we have something like a wave equation acting on the constraints with this source function here. So if we start with initial data that the constraints are initially 0 and their time derivatives are 0, this should say that they should remain 0 for all times. So that's good, and that means we can basically just use this evolution equation here, and as long as we start off with good initial data that solves the constraints, then we will be solving Einstein's equations. So in practice, actually checking that this condition that basically CA equals 0 for all time holds true is actually a very non-trivial check that people do all the time to basically ensure that when they're carrying out these numerical simulations that basically they're doing everything correctly. So I mean, you can notice that basically if you do almost anything wrong, if you don't solve the initial constraint equations, the Hamiltonian momentum constraint, then that will not be satisfied. Even if you basically, so if you don't use the right evolution equation, of course that won't be satisfied. Or even if you try to couple your metric to some stress energy tensor, and that stress energy tensor doesn't satisfy stress energy conservation, then again you'll also get this constraint violation. Yeah, so in practice, what people do is they'll look at the norm of their constraints as a function of time, and they won't exactly be 0 because there'll always be some sort of truncation error, but you'll see some behavior at maybe low resolution, and then you'll increase the resolution and see that it's decreasing in some prescribed way. Basically, that as you increase the resolution, this quantity is converging towards 0, and therefore you convert. Like
the norm of the.
Yeah, the norm.
Yeah, okay.
Yeah.
Should one check like the constraint actually globally and not the norm, because maybe you have a point? Could you have some?
Yeah. So I guess norm here, I mean take add up all some absolute value of the components and then integrate it over your whole domain.
Yeah.
But yeah, you want it to be satisfied throughout the whole domain.
Okay.
Any other questions?
You don't keep track of momentum and Hamiltonian constraint anymore in this way?
Yeah, you could also evaluate those. Yeah.
Does this C constraint already inherits 2 of those? How many? So I'm trying to figure out in this picture. One of them is replacing the gate choice of choosing time foliation.
Yeah, so basically we're basically choosing the 4 coordinate degrees of freedom by specifying these 4 source functions. Yeah, and so you can kind of think of them as sort of setting the evolution of the lapse and shift.
And then one lapse and shift and one for the foliation. And so instead of choosing my time foliation, which you don't fix it anymore, right?
I mean, these these gauge conditions still will set, how your time slice evolves forward and which slices you're choosing through your four-dimensional space-time manifold.
What do they
So I mean, I guess it's a little harder to exactly translate some, gauge condition on like sort of the Laplacian of the coordinates. So in the homework, you'll actually work out a couple examples of, for example, what it means to be in a harmonic gauge for like a FRW spacetime and also for a black hole spacetime. Yeah, so like, actually, it turns out for a lot of applications, you don't necessarily want your force function, you don't want to exactly be in harmonic gauge, but sometimes you want to basically require coordinates to satisfy something like a damped wave equation. You don't want your coordinates themselves to be too dynamical. So a very popular gauge is called so-called damped harmonic gauge. Yeah, so we're done, right? So we came up with this hyperbolic equations, and now we can just use these to, evolve binary black hole spacetimes, right? So it actually turns out that that's not true. It's not quite all the pieces you need. If you actually do one of these convergence plots, for example, with a black hole, what you'll find is that basically your constraints will basically blow up with time. And you can increase the resolution, so you start with even smaller amount of constraint violation, and it will be smaller, but it'll still blow up in time. And as you decrease the resolution, you maybe can evolve for a little longer before your system, you don't trust your simulation anymore, but it'll still blow up. And the problem is not really sort of an inherently numerical one. The problem is basically that this CA equals 0, this constraint preserving manifold, is actually unstable in sort of the whole space of solutions to this generalized harmonic evolution equation. And this is not quite the same as the system not being hyperbolic. This growth is sort of controlled by the properties of the background solution. For example, the black hole mass or something like that. But it still basically means that you can't use these to evolve very far before they become untrustworthy. So the solution that people finally used to fix this problem is to basically modify the behavior of these systems of equations off the constraint preserving manifold. So does anybody have an idea of what we might do then? I think Louise kind of alluded to this in the previous lecture. So the basic idea is that we want to add something to this equation star that will make our constraint-preserving manifold stable. So it turns out what does the trick is something like this. So this is just proportional to this constraint violation. So basically, if I had a perfect solution for the Einstein equations, I'm just adding 0 to my evolution equations. I haven't changed what happens. But the trick is that now if I crunch through and determine how this equation becomes with this additional term, now it looks something like this. So basically, in addition to this like nonlinear stuff, which may cause this, cause some problem with the constraints, I have basically something that looks like a damping term. It's like sort of roughly like the time derivative of the constraint violation, and this kappa is just some dimensionful parameter. And basically, you can see from this that kappa is going to have basically the dimensions of 1 over length or time. And so basically, this term will damp violations of this constraint on timescales of 1 over kappa, or equivalently, it will damp constraint violation with wavelength 1 over kappa or larger. Yeah, so like in practice, in order to get things working, you want to set this kappa to be something like 1 over the mass of your black hole in your system, or basically roughly equal to the sort of characteristic length scales of the problem you're interested in. So any questions about that? Yeah, so any questions?
I'm just trying to see directly from that equation, why is that a damping term? Like I can see, okay, if C is not 0, this would give me like something negative that will damp my C to be 0. I'm trying to see it explicitly, but I don't know if I can from that form.
Yeah, I mean, yeah, so you can kind of, work through it, but basically this is something like just the wave equation here, and then remember this is basically just picking out the time component of this. Yeah, and then basically want this to be positive. Okay, so now we're going to sort of switch topics and talk instead about apparent horizons. So, all this week we've been talking about sort of evolving Einstein's equations, starting with some data on some time slice, and then evolving the metric to subsequent time slices. So sort of to go along with this, we need to be able to define black holes in dynamical settings. So far we've only talked about Kerr solutions, which basically exist for all time. They're unperturbed black holes, but if we want to go to what happens when two black holes merge or some matter collapses down to form a black hole, we want to be able to define black holes in a dynamical setting. So the sort of definition we've been using so far for black holes has been to determine the boundary of a black hole has been the event horizon. So the definition of the event horizon is it's the boundary of the causal past of future null infinity. So sometimes people write it like using the following notation, where J minus just means the causal past, and then we use scribe plus to indicate future null infinity. And so basically we take our manifold and we subtract this part, which is outside the event horizon, and then our black hole is the remaining part of our manifold. And then the event horizon is just the boundary of this. So sort of less formally, if we want to determine where the event horizon is, we basically follow light rays from the vicinity of our black hole, and the ones that can escape to affinity, that's future null infinity for light rays, are outside the event horizon, and the ones that can't escape are inside the event horizon. So we can make that a little more clear by drawing a Penrose diagram. So let's say we're in the situation where we have some, matter that's spherically collapsing down to form a black hole, and we get the following Penrose diagram. So we have our, let's say this is the outer boundary of our matter. It's going, it collapses down. This is space-like infinity, past null infinity, and future null infinity. This is the singularity inside our black hole. And then, of course, the event horizon is this line here, where, again, we just take future null infinity, look at its causal past, and the boundary of that is the event horizon. Now, there are a couple of reasons this sort of definition of a black hole is not ideal for dynamical settings. So one problem is basically, we need to figure out, the entire future of our space-time in order to be able to define this event horizon, right? If we just know sort of some part of our space in this, we don't really know where future null infinity is, and we can't determine where the event horizon is. We need this whole structure to define it. So in particular, if we're, doing a numerical evolution, and we're just at some particular time, we can't tell if we have an event horizon yet. We only know when we're sort of computed the whole thing where the event horizon is. So that's not very useful. The second problem is that the event horizon is teleological. So it's a word I've actually only heard in relation to describing event horizons. But basically, the event horizon sort of anticipates the future. So if we look at this example of a collapsing shell of matter, even before the matter has collapsed down to the point where we have some matter that's less than, the radius at which the matter is collapsed is less than 2m times the amount of matter, you will already have started to form an event horizon at the center, right? And that's basically because the event horizon knows that if you start with some light ray that's very near the center, initially it'll be able to go radially outward. But it knows that in the future, this matter is going to collapse down more, and so the light will not actually be able to escape out to infinity. It'll be able to go outward a little bit, but then it'll get trapped and it'll never make it out. So the event horizon, in some sense, anticipates the future. So in sort of to address these, we're going to introduce the concept of an apparent horizon. So in order to define an apparent horizon, we'll need a couple of auxiliary definitions first. So we'll choose some time slice. We'll call it sigma t. And then we will choose S to be a closed two-dimensional space-like surface. That's contained within our time slice. So we're two-dimensional surface S, and then we'll define QAB to be this induced metric when you just restrict to the surface. And then we'll also define L to be a vector that's normal to our surface. So for the apparent horizon, we're going to take L to be a null vector. Sorry, before I get to that. Yeah, so L is a normal vector field on our surface, and then we can use L to define what we'll call the expansion, which we'll denote with the script O. So it's the Lie derivative with respect to L of the log of the metric determinant of this induced metric Q, basically the volume element. And so that's actually equal to just this. So basically, this is just the fractional change in area of the surface S when you move in the direction L. So that's what we call the expansion. So for our apparent horizon, we want to take L to be null. And there's two directions we can take, inward and outward. So we'll define L in terms of basically two normal vectors that are time-like and space-like. So here, NA is just the usual normal vector, unit vector that's normal to our slices of constant t, so normal to this sigma t. And then SA is just the space-like vector that's normal to our surface S. And then the plus and minus correspond to the outward and inward null vectors. And taking the normal conventions, this allows us to basically normalize our null vectors. Because with these definitions, this is time-like. Take this to be normalized and space-like. And so, of course, if you contract either the plus or minus with itself, we get 0 because they're null. But if you contract them with each other, then you get -2. Yeah, so in terms of this vector L, we can now compute an expansion. So we can call the outward null expansion as just the script O evaluated for L plus. And if we work out what that is, we actually get something like this in terms of the usual 3 + 1 variables. So just the divergence of the space-like unit normal, then this is the extrinsic curvature contracted with these space-like unit normals, and then the trace of the extrinsic curvature. So you can just work that out from, basically what you get when you act with these various, with the covariant derivatives on these two different vectors. Yeah, so we're almost done here. So now basically, if we're in the situation that the outward null expansion is less than 0, we'll say less than or equal to 0, everywhere in our surface S, we're going to call S an outer trap surface. And we're in the marginal case where this is just equal to 0, then we will call this a marginally outer trap surface. Which we can just abbreviate as a MOTS. And what we're calling the apparent horizon is just the outermost marginally outer trap surface. So the reason I said outer twice is basically for a given time slice, we can have multiple marginally outer trap surfaces. But if one is contained with another one, we'll take the outermost one, the apparent horizon. So this differs slightly from the original definition that Hawking gave of apparent horizon, which is similar, but basically is just the boundary of the trapped region. And the trapped region is just a region where any given point is contained on some surface that's trapped by this definition.
Should the areas of these apparent horizons always grow too, as like in the
Yeah, you can work out a sort of area increase law for these dynamic horizons as well.
How do you do it, like numerically, like in a 3D setting, to actually find these surfaces? It looks hard.
Yeah, there's a couple of different ways of doing it. So basically, one of them is you start with some guess of what your surface is. You compute the outward null expansion on that surface, and then basically you basically see how big it is at every point, and then you flow that surface a little bit to basically try to find where it equals 0. So if you're sort of outside, you want to flow inwards, and if you're inside, you want to flow outwards. And basically, how much you flow at every given point on your surface should be proportional to how big this null expansion is.
Okay.
Yeah, there's also a way to do it. That's sort of like get something like a parabolic equation. You can also solve some elliptic equation to look for these in general. But yeah, you basically need to know what the surface looks like. Yeah, and so sort of physically, what this means is that an apparent horizon, if you want to determine if you're on the surface of an apparent horizon, you basically shine light outward at every point, and the light can move outwards and expand, and then you're not inside an apparent horizon. If it has to fall inward, then you're on a trapped surface. And if you're marginal in between, where the light just sort of hovers there momentarily, that's the surface of an apparent horizon. Yeah, and so this whole definition depends on our choice of the time slice. So it is possible to sort of choose very weird time slices, so that, for example, even if you were in a Schwarzschild spacetime, there wouldn't be an apparent horizon. So those are kind of pathological examples, but this definition is sort of time slicing dependent. However, one can sort of stitch apparent horizons at a given at a set of time slices together to form some world tube, and then work out this concept of a dynamical horizon, which is basically just like a union of these apparent horizons, where each slicing gives some space-like world tube. And then one can define sort of equivalents of these black hole thermodynamic laws for these dynamical horizons. And you should also note that as long as, assuming some reasonable conditions, for example, we have cosmic censorship, so we can, evolve for our whole space-time, and like the null energy condition, one can actually prove that if at a given slice you have an apparent horizon, then it'll actually necessarily be contained within the black hole as we first defined it. That's the slice of basically taking the event horizon and taking a time slice through it. So the apparent horizon basically has to be contained within the section of the event horizon on a given time slice. Yeah, so just briefly in the last minute or two.
Very well.
Yeah.
Is there an easy example or straightforward where you can see that you have multiple apparent horizons nested one within the other?
Yeah. So if they're nested, you can have multiple marginally outer trapped surfaces, and then one of them will be the apparent horizon by definition. So one example of that where that happens is binary black hole merger. So let's say you have two black holes, they come together, they collide, they merge into one black hole. If you look at the event horizon, you get something like this, what people call a pair of pants diagram, right? Where you sort of have the event horizon of one black hole, it comes up, it joins with the other, and then you have so here, time direction is upwards, and this is some spatial direction. And because sort of the definition of the event horizon, these have to join together. It's one connected structure. But if you look at what happens when you track the apparent horizons, so let's say you're at some time right before they merge into a common horizon. So you'll find, the black hole, the two apparent horizons of the black holes, they'll be next to each other at some time slice. Then when they get close enough, you'll see something like this. So here, this is apparent horizon 1, 2, and then you'll just pop up a common apparent horizon. And then, but these, what were just a small time ago, the apparent horizons will still be there. They'll still be marginally outer trapped surfaces. But they'll just be contained within a common apparent horizon.
They don't open and join?
Yeah, actually, so what actually happens for these guys after this common apparent horizon forms, people still are trying to figure out. Actually, there's a very interesting paper that Eric Schneider and some colleagues put on the archive last night, trying to figure out exactly what happens to these guys and suggesting that in fact these guys do merge together. But normally people, as soon as they find this apparent horizon, then they don't really care what happens inside.
What do you just excise outside of that or something like that?
Yeah, so one uses of finding these apparent horizons is basically, once you find them, you can excise regions within the interior, and then sort of by the definition of apparent horizon, information won't propagate from inside these to outside. So it's okay to sort of evolve your equations just outside without imposing conditions inside. Yeah, so I think that's it. So any other questions?
Yeah, so the only reason that you would need to know where the horizon is just for the excision. If not, you wouldn't really need it, and you could wait until having a stationary solution and then track back and say, oh yeah, this was my horizon in this situation. Could you do that or no?
Yeah, well, I mean, like, so if you want to find event horizon or something like that, yeah, you want to basically have, so usually actually the best way to do it is like you evolved at some very late times, you seed some null vectors, some like null geodesics sort of very far away, and then you track them backwards and see, yeah, which like how close they can get. Or you could try the other way, just seed some null geodesics and then evolve them forward and for long enough to see which ones escape and which ones don't. But yeah, I mean, besides like sort of knowing where to excise, there are also sort of very good diagnostics of what's going on, like understanding the dynamics of the space-time. You can define some, you can calculate their area, and that'll they'll give you an irreducible mass. You can, if you're in an axisymmetric setting, you can define an angular momentum that's associated on these horizons. You can calculate fluxes of your matter through them. So there's sort of very useful things to keep track of. Any other questions? Okay, so tomorrow we'll talk about how to actually solve these constraint equations, the Hamiltonian momentum constraints.